And when it bounces off, it makes what we call a supernova. So that's an explosion. So that's really what's going on. So inside a star, we have this huge explosion. And that actually came from this material coming in, bouncing off the solid core, and basically flying outwards. So when we do that, we have this huge explosion. In this explosion, it can make iron plus heavier elements, it turns out. This is what the explosion does. So in that explosion, then there's enough energy in order to make all the heavier elements. So we've basically accounted for all the elements. Think about it. The Big Bang made the hydrogen. Stars are making everything heavier than hydrogen all the way up to iron, but no higher than iron. Then we have a supernova that makes iron plus a bunch of all the heavier things actually that we find. Almost all of them are made in supernovas. And what's really interesting is this. In the supernova, that means it actually spreads out the material. So that means that all those materials that were made end up being sent outwards. So that means, now this is actually a real picture. This is a picture of one called the Crab Nebula. Now nebula just means like a cloud. So anytime, early astronomers were seeing things that looked cloudy, they called it a nebula. But a nebula can be so many different things. And this particular one, it's been named Crab. I'm not sure. It doesn't really look like a crab to me. But it turns out they've named it that. And what is kind of neat about it is this, that this one right here was actually, we think it was a supernova that happened in 1054. How in the world do we know that? Well, the Chinese were very good at mapping the sky and saying what happened. And they have very clear records that show that in 1054, around a certain spot in the sky, they said that things were really, really bright. In fact, it was nearly as bright as the moon. So that was something that was very bright in the sky. They wrote down where it was and when it happened. And it turns out that now, if you look with a high-powered telescope where the Chinese said to look, you see this. So we think that what happened was there was a star in the middle. I'm not sure exactly where it is, somewhere in the middle. It actually blew up. And when it blew up, it made this giant, really bright explosion. And what we're seeing now is the remnants of it. We're seeing the leftovers from that cool explosion. Isn't that awesome? And it turns out there's a star in the center. It's a neutron star, and we call it a pulsar because it's spinning super, super fast and sending out a signal every, many times per second. So I think that's really, really cool. So the supernovas themselves, they are responsible for making iron and heavier elements, but also they send all those elements out. They just spread them all out. So we've just been looking at how the elements were made. And like I said before, the Big Bang, it made the hydrogen. Next came the stars, which made helium, everything heavier up to iron. And the supernova makes iron and heavier things and spreads the material out. What happens next? How does it make the Earth? Well, that's when you have to actually make the sun and the Earth. So what can happen then is that these things can actually coalesce. So this is an example of a nebula. It's called the Eagle Nebula. It turns out in there's a bright, bright star, and what it's doing, it's pushing out a lot of material, and that material is being sort of squished. So what it's doing, it's taking hydrogen gas that's floating around in space, and it's squishing it. And as it gets squished, it gets hot, and it actually gives off light. So it makes this really pretty sort of pattern here. So you can look it up. It's called the Eagle Nebula. This is a large-scale version. But look at this beautiful picture. This is one of my favorite astronomical pictures. What this is a small section of this one. Look carefully. In this picture right here, if I take this, I want you to look at this piece right here. This column and this column and this column. Turns out if I take this and I sort of rotate it like this right here to make it sort of standing straight up, do you see how this piece right here, if I did a zoom in, so let's just say I took this right here, what that is, that's this. Isn't that awesome? So what they've done, they took a really zoomed in version of this thing and it looks like this. So it turns out what's happening then when this gas gets squished, at the very edges, you see these little things sticking up like that? Those are new stars that are about to be born. Because that hydrogen gets squished, and when that hydrogen is squished, it gets hot enough and dense enough to make a new star. So you see, we think that this happened with us. We think that our own sun, oops, I don't think I made that very clear at all. But our own sun, what happened, we think, is that it actually came from something like this. So a supernova came out and actually squished the material and also added extra material. So you see that extra material like the iron and all the other stuff also came in here and then basically caused the hydrogen to squish and it made a star. And the leftover stuff that made up the star ended up making planets, and that made us. So we think we have an explanation for how we got here. Literally, all the pieces that are making up us, we think we are star stuff in every sense of the word. We think that every single thing that makes you came from a star. So all the material in you came from a star. Isn't that cool to think about? Like your left hand, like the material in your left hand was, very likely made from different stars than your right hand. I mean, think about it. The iron that's in your blood, for example, we have lots of iron in our blood. That was made in a supernova explosion. The calcium in your bones was made in a star. All the material that makes you came from a star. How cool. And because of that, we really are connected to the stars and to the universe. So when we say we're made of star stuff, we're not exaggerating. I think that's really, really interesting. And in fact, we're expecting that all other life in the universe is also made in a similar way. We say, it should be universal, should happen everywhere. So I think that is a really profound statement, and I think it's really, really interesting. So next, what can we do next? Well, next what we can do is actually talk about how we actually define life. Because if we're going to look for aliens, or we're going to look for life on other planets, we'd better know what we're looking for. So what do we mean by alive? What do we mean by life? And this is, you would think that we've got this figured out by now, but it turns out this is not an easy thing to define. Because, see, what happened is a lot of different scientists are at odds with each other with as far as what the definition should be. Now, this is really fundamental. I mean, it turns out there was, one probe, for example, called Viking. That was a robot that landed on Mars looking for life there. And it had a little scoop, and it actually scooped up some dirt, put it onto its back, essentially, cooked it up, and then saw the results. And the results were, we're not sure. Because they weren't entirely sure what they were looking for. So, and believe it or not, we're still having trouble with defining exactly what life is. So a lot of biologists, and these are the people one should probably ask, they've actually defined it based on, now it turns out no matter where you look, there's so many different definitions for life. But most of them have these 6 things in common. So a lot of biologists will say, okay, something that is alive has to have some sort of order to it. It has to be some sort of regular shape or something like that. So there has to be order to the thing you're looking at that's alive. It also has to be able to reproduce, so to make more. It also has to be able to grow and develop. And it has to use energy. Next, it has to respond to the environment. So if you do something to it, it usually responds in some way. And finally, there has to be evolutionary adaptation. We're going to talk more about evolution in just the next couple of videos. But it turns out that these 6 definitions, I mean, maybe if something's alive, it has to follow all 6 of these. But it turns out each of these by themselves is a weak statement. And what's kind of a fun exercise is that you can actually take each of these by themselves and come up with things that are not alive that follow this. And I think that's a really fun exercise to do. So you can try to think of, what's something that's not alive but that has order, or something that's not alive but uses energy. So it's kind of a fun thing to do, to try to think of, to find holes with this sort of definition. But it turns out maybe all 6 of them together, maybe that makes something alive. It turns out if you ask a physicist, we have a nice, neat definition. It's all based on something called entropy. So it really depends on who you ask with what's alive. And I think that's really, really interesting. So if we're looking for life on other planets, we need to make sure we know what life means. And that is precisely one of our big challenges right now, is actually defining what life is. Because we have other robots that are driving around on other planets right now, and they're looking for life. So they're looking for these types of signs here. Now, how did life actually start on Earth? This is the next important question I think to ask, is how did it start? But before we can talk about how it started, I think it's important to focus on when it started. And that's going to help to illuminate a little bit about what we're going to talk about. Haha, illuminate and stars. I just realized I made a stupid joke. So I'm going to give you an extremely brief history of the Earth. Very, very, very brief. So I'm going to skip lots of steps, but I'm just going to give you the key things that we need to know. So first of all, how do we know about this stuff? Turns out we know evidence based on rocks, based on meteorites, so things that have come from outer space into our atmosphere that we found on the ground. And we can also do a lot of this stuff based on crater counts, so counting, these holes or these dents in other planets or even moons. Now, we think that the Earth is around, this is actually pretty interesting, we think that the Earth is around, I'm putting this little squiggly equal sign, it's like roughly 4.5 giga years old. Now what does giga years, what does this G mean? You might think about it with computers, if you have gigabytes of RAM, for example, or things like that. What giga means is billion. So 4.5 billion years old. That's how old we think the Earth is. And again, we can guess this based on geology and also based on these meteorites that we find. So now, so the Earth is around 4.5 billion years old, but how was the Earth formed? Well, here's what we think happened. Extremely brief history. Here we go. So first of all, like we talked about before, you probably had a nebula, and that nebula could have been squishing the material. So it turns out this is a really nice one. It's called the Orion Nebula. So if you look in Orion, remember I was showing you that constellation before, and I talked about Orion's sword, or his, whatever else you want to call it. Turns out if you zoom in on that, you get this pretty picture. But within this, scientists have found a bunch of these little things like this. And these are actually called protoplanetary disks. So that's what these right here are. So those are called protoplanetary disks. And that's why they're actually called like proplid for short. So protoplanetary disks. So these things, those are sort of beginning stars. These are like beginnings of solar systems. So that material, now if we actually zoom in, it turns out this one has lots of them. So we can look at lots of these other protoplanetary disks. So what's happening is that this material that's being squished in the center, it's hot enough to make a star. So the star sort of lights. So now you have a star that's converting hydrogen to helium. But you have a lot of extra material out there. Now that material ends up coalescing because of gravity. It ends up coalescing and becoming things like planets or comets or asteroids. So in our case, we think the Earth was formed like this, where the sun that was made in one of these protoplanetary disks, the extra material made other planets, including the sun. And all that stuff also made you.